Greetings to all, dear students. So today we are going to learn about harmonic function. Okay, so this is the last section in the first unit. Okay, so okay, harmonic functions. When we say that a function is harmonic, if dou square u by dou x square plus dou square u by dou y square will is equal to 0, then we say that a function is harmonic function. So whatever the function we are taking, if double derivative of that function with respect to x and as well as with respect to y is equal to 0, then the function is called harmonic functions. So here, let u of x comma y be a function of two variables x and y defined in a region D. So we are taking a function with the two variables x and y. And the function is said to be a harmonic function if dou square u by dou x square plus dou square u by dou y square. Since the function is of two variables x and y, we are differentiating with respect to x as well as with respect to y. Okay. So if dou square u by dou x square plus dou square u by dou y square equal to 0, or we can say this as u double xx. That is, 1 minute. That is u xx plus u y y equal to 0. Okay. Instead of writing dou square u by dou x square, we can write it as u xx plus u y is equal to 0. If this satisfies, then we say that the function is a harmonic function. Also, this function is called as Laplace equation. Okay. So I hope the definition is clear. Okay. So a function, any function, okay, any function with the two variables x and y is said to be a harmonic function if dou square u by double derivative dou square u by dou x square plus dou square u by dou y square is equal to, it should be 0. Okay, so consider the following example. So consider the function u of x comma y is equal to x square minus y square where x not equal to y. So we need to find out ux and u double xx as well as uy and u double yy. So first we find out dou u by dou x, this is equal to 2x. Then again when we derivate with respect to x, we get the answer as 2. Similarly, dou u by dou y is equal to minus 2y. When we again derivative, we will get minus 2. So sum of dou square u by dou x square plus dou square u by dou s square will become 0. So then therefore we can say that the given function is a harmonic function. Okay. Next theorem, we can say this is an important theorem. Okay, because this theorem gives a necessary condition for a for the real part or imaginary part of a function to be analytic something. So, okay, so this theorem is a very important theorem. The real and imaginary part of an analytic function are harmonic functions. So if we have an analytic function, then the real and imaginary part should be a harmonic function. This is what this theorem meant. Okay. So the real and imaginary parts of an analytic function are harmonic functions. So for that, we are taking an analytic function f of z. So f of z equal to u of x comma y plus I into v of x comma y be an analytic function. We need to prove the real part and imaginary part. That is, u of x comma y plus I into v of x comma y are harmonic function. That is to prove dou square u by dou x square plus dou square u by dou y square equal to 0 and dou square v by dou x square plus dou square v by dou y square equal to 0. Okay. So since f of z is analytic, we know that it satisfies the Cauchy-Riemann equation. That is ux equal to vy and uy is equal to minus vx. So now we consider dou square u by dou x square plus dou square u by dou y square, and we prove that this value is equal to 0. The dou square u by dou x square can be written as dou by dou x into dou u by dou x plus dou square u by dou y square written as dou by dou y into dou u by dou y. Using CR equation, dou u by dou x become dou v by dou y and dou u by dou y becomes minus dou v by dou x. So it is equal to dou square v by dou x dou y minus dou square v by dou y dou x. So here we are derivating with respect to x first and then y. Here we are derivating with the, in the first one we are derivating the function with respect to y, and then next in the second one we are derivating the function with respect to x first and then with respect to y second. Okay. If both are equal only, the value will become 0. So by Squat's theorem, the value of these two is equal to 0. Okay. So let us see what is Squat's theorem. Okay. If a function f has continuous second order partial derivatives in an open region of the plane, then the mixed partial derivatives are equal. So what this theorem says, if a function f has continuous second order partial derivatives. Okay. So here we are taking the second order derivatives by which one? Yeah, using analytic, we can say that the first order partial derivatives are continuous. Also, we can say that second order partial derivatives also continuous. If this true, then the mixed partial derivatives are equal. That is, dou square f by dou x dou y is equal to dou square f by dou y dou x. So using Squat's theorem, we can say that these two values are equal. Therefore, dou square u by dou x square plus dou square u by dou y square equal to 0. Similarly, we can show that dou square v by dou x square plus dou square v by dou y square is equal to 0. So therefore, if the function is an analytic function, then the real part and the imaginary part are satisfies the satisfies the condition for harmonic functions. Okay. So the real and imaginary part of an analytic function satisfies the condition for an harmonic function. Okay. So next remark. The Laplace equation provides a necessary condition for a function to be the real or imaginary part of an analytic function. Okay. So, what does this mean? Suppose we have an analytic function and suppose being given the function u of x comma y or v of x comma y. We can check that whether this real part is real, it will be the real part of an analytic function. Whether this function will be a real part of an analytic function, or whether we can check whether the function b of x comma y can be an imaginary part of an analytic function. So this equation, if it is analytic function, then the real part and imaginary part are harmonic function. Using this theorem, we can check that whether a function u of x comma y or v of x comma y can be the real or imaginary part of an analytic function. If it is the real and imaginary part of an analytic function, then it must satisfies the harmonic function. The condition for harmonic function. If it is not satisfying the condition, means then we can directly say that the function u of x comma y or v of x comma y cannot be the real or imaginary part of an analytic function. I hope it's clear to you all. So consider the example u of x comma y is equal to x square plus y. So we are checking whether this function satisfies the condition for a harmonic function. So dou square u by dou x square equal to 2, dou square u by dou y square equal to 0. When we add these two, the value is 2 not equal to 0. So therefore this function cannot be the harmonic function. Since it is not a harmonic function, then we can tell that this cannot be the real part of an analytic function. If it is a real part of analytic function, then it must satisfy the Laplace equation. Since it is not, we can say that this function is the function cannot be the real part of an analytic function. Okay. So with this, I end this video. The next video, we will see the definition of harmonic conjugate and the problems to find out problems regarding they will give one analytic function, sorry, real part or imaginary part of an analytic function. From that part, the real part or imaginary part, we are going to find out the imaginary part or real part. That is, if they give the real part, we will find out the imaginary part. If they give the imaginary part, then we will find out the real part, and then we find the analytic functions. Okay. So in the next video, we will see that those things. With this, I'm going to end this video. Okay. So thank you all. I hope the concept is clear to you all. Okay. Thank you.